Welcome back, everyone. In this lesson, we will discuss limits involving infinity. Now, if you recall in the very first lesson about limits, I introduced you to a motivating idea. We talked about polygons that are getting with more and more size that are covering a circle perfectly well. So this was the idea from Archimedes, right? So if you take a polygon and to try to figure out the area of a circle. And then if you are able to increase the number of sides, sorry about that, polygon didn't look that great, but if you increase the number of sides, these gaps are going to get smaller and smaller, right? So the idea there was to let, if A sub n represents the polygon with n sides, ultimately, so you would find the area of a polygon that fits into that circle with five sides, 6 sides, 12 sides, and so forth. But ultimately, to find a perfect coverage, we discuss the importance of knowing you have to find the limit as n goes to infinity of A sub n. And this actually is going to give us the perfect coverage A. So let that be our motivation to understand why we need to study limits as n goes to infinity. I'll give you many more examples of this. You will see it as you study calculus further. Like when we do area under a curve, we're going to use little rectangles and we're going to find the area under a curve by finding area of, let's say, n rectangles. And then the exact area is going to be, once again, limit as n goes to infinity of A sub n. So as n goes to infinity, you're going to have more and more rectangles. These overflows and underflows where the rectangle meets the curve are going to get smaller and smaller. In the limiting case, we're going to find a perfect area. As a matter of fact, that is such a important underlying principle of calculus. I cannot really emphasize how many times you're going to be using this limit as n goes to infinity concept. And really the general let me give you a little secret here. And you can really summarize calculus, or one branch of calculus, the integral calculus, pretty much to the following. Take a difficult problem, chop it down and slice it down into smaller problems, such as instead of finding area under a curve, we're finding area under a rectangle, which is a simpler problem, right? And then through using the concept of a limit as n goes to infinity, solve the original question. In this case, you would have to know how to find the limit of a sum, of course. I'll give you one more example, and then we're going directly into examples using limits with infinity. So let's say that you want to find the arc length. So you could do the same principle. You could split that into little, tiny little segments, where these segments are so small, if you look at them, they will be almost a straight line. And we know in large view, a straight line, we know how to find the length of that, right, using the Pythagorean theorem. If you know, let's say this is change in x, delta x, this is change in y, delta y, you could find that one as a square root of delta x squared plus delta y squared. So we know how to find the answer to the simpler question, that is to find the length of a line. And from there, by taking a limit as number of segments go into infinity and adding up the lengths of those line segments, you could find the actual length of the entire curve. Same goes with volume, and you're going to see this used in so many different situations. Finding the limit as n goes to infinity is going to be essential in solving an important, meaningful calculus problem. But for now, we're going to go to some of our basic examples where there's not so much meaning associated to it as we just want to get the hang of it, understand how do you find a limit as n goes to infinity, so when the time comes, we know exactly how to handle that situation when we're doing more meaningful problems with applications. Let's begin with the easiest problem that I can think of, and that is the function y equals 1 over x. Okay, so 1 over x, most of us hopefully remember the graph. You have a part in the first quadrant and also a part in the third quadrant, right? So if you graph this, you're going to have x equals 0 as your vertical asymptote, right? Because it's not defined there. So we could graph it in the calculator, but we don't need to. This is a simple enough one. So let's just start getting some practice now. How do you find the limit as x goes to infinity of 1 over x? So again, x goes to infinity, meaning x gets larger and larger without a bound. So if you follow on this curve, x values, look at what's happening to the y values. As x gets larger and larger and larger, what is happening to the y values? They're getting smaller and smaller, right? So in the limiting case, they're approaching towards 0. So this limit is going to be 0. Okay, what if x is going towards negative infinity? Follow on the same curve, y equals 1 over x. As x goes towards negative infinity, look at where the y values are approaching. That is also 0. Okay, here's a different question. As x goes to 0 from the left-hand side, so as we approach the 0 from the left-hand side, these are the points on the curve that we're following. Look at what's happening to their y values. These are getting lower and lower along the y-axis, right? Therefore, their y values are going towards negative infinity. And then this one is x goes to 0 from the right-hand side. So approach to 0 along the curve from the right-hand side. What is happening as x goes towards 0? What is happening to the y values? Going towards positive infinity. So in general, what could we say is as x goes to 0 of 1 over x, we could say the limit does not exist, right? Coming from the left and coming from the right, we do not get the same value. Now, your textbook or some textbooks, even when the limit is infinity, say positive infinity, they might say the limit doesn't exist, meaning that the limit is not a finite value. Now, I prefer to see whether it's plus infinity or minus infinity, so I'm not going to use the terminology does not exist. If that's the answer, I'm going to use the terminology if it truly diverges, meaning that it, like one part maybe goes that way, one part goes the other way, they're not going in the same direction. That's when I'm going to use it doesn't exist. But technically, you could say the limit does not exist, or it's not finite in a situation like this. Um, And there's another word. I could also say the limit diverges. If the limit does not go to a finite value, if it's an infinite value, we could also use the terminology diverges. Like in this case, the limit converges to 0 if it's a finite value. If it's infinity, it diverges. So through this very, very simple example, we've already seen a few things. So for instance, you could be taking a limit as x goes to plus or minus infinity, or your final answer may turn out to be plus or minus infinity, depending on the question. So in this section, we're going to deal with both kinds of problems, whether we're taking a limit as x goes to infinity, and sometimes the final answer may turn out to be infinity. All right, here's another example. Given f of x equals x over quantity x minus 3, let's go ahead and determine the limit first as x goes to 3 from the right, then to 3 from the left, and as x goes to 3 in general. My suggestion for you here is if you can, start with a basic graph. If you have your graphing calculator, go ahead and use that. If you can figure it on your own without it, even better. And if not, use desmos.com, and then we'll come back and discuss the solution. So when you look at the graph, and if you try to do this without a calculator, first you will need to graph the vertical asymptote where the bottom is 0, that's x equals to 3, and the horizontal asymptote, and that will turn out to be y is equal to 1. I'll give you more reminders about that later on. That turns out to be the ratio of the leading coefficients when the degree of the top equals the degree of the bottom. And then you're going to find that if you plot it even a few points into this function, let x be, let's say, a number greater than 3, let x be a number less than 3. With a few extra points, you could actually see that the graph, one piece is going to be over here, and the other piece, I believe, is going to be over here. All right, so based on that graph, let's answer the questions. What is the limit as x goes to 3 from the right-hand side? There the points are rising along the curve, right? So that goes towards infinity. What's the limit as x goes to 3 from the left-hand side? There the points are falling as we approach the x equals to 3 along the graph. So that's negative infinity is where the y values are approaching. And in general, what is the limit as x goes to 3? One side is going to infinity, one side is negative infinity. So there I'm going to say the limit does not exist. All right, let's do a few more examples involving limits with infinity. So this time I'm going to take a limit as x goes to infinity of sine x over x, and also as x goes to negative infinity of the same function. Let's think for a minute about what the graph of this function might look like. Sine x is the oscillating function, right? We learned in trigonometry, of course. So we should have a pretty good understanding of what that graph looks like. So from 0 to 2 pi completes one full cycle. But sine x over x, that will still have oscillations, but what happens is as x gets larger and larger, now because sine x is always bounded between 1 and negative 1, so the top is bounded, but the bottom gets larger and larger. So any idea what's going to happen to the ratio? So that will go towards 0, right? And if you look at the graph, this is what the graph looks like. So this is the point 1. So at the top, sine of 0, as a matter of fact, if you look at it very carefully, you're going to find that right at that point, there is an open point, meaning it's not really um, defined at 0, because you have sine of 0 over 0, which is indeterminate form, and you would, in another problem, we're going to explore the situation right around 0 a little bit better. But just at the moment, know that this corresponds to 1, and then the oscillations are dying, and right now we're taking a limit as x goes towards infinity. So eventually these oscillations are going towards, like, it's just going to oscillate almost entirely closer and closer along the x-axis, so the limit is going to be 0. And what happens is you go towards x on the left-hand side along the curve. Again, once again, oscillations are dying. Same thing happening there. It's going towards 0. As a matter of fact, if you did not graph this function, you can still get an answer because you could have rationalized it as follows. You could say, okay, sine x over x. I know that that will always be between negative 1 over x and positive 1 over x. How do I know that? Because sine x is between negative 1 and 1, right? And now take a limit of each side as x goes to infinity. So take a limit of the left-hand side and also take a limit of the right-hand side as x goes to infinity. So what is the limit of this? If you look back to the problem from the first page, you're going to see we said that was 0 and negative 1 times 0. That's just going to be 0 because the bottom keeps getting larger and larger. A constant over a quantity that keeps getting larger is getting smaller, going to 0. And at the moment, I'm going to leave the middle part as it is. And the limit of the right-hand side is also going towards 0. So technically, I took a limit of all three sides. So ultimately, you have a quantity here that's between 0 and 0, so therefore it must be equal to 0. And that's another way to explain our result over here. As a matter of fact, what we just did here is called the squeeze theorem. So while we're at it, let's take a quick look. It tells us if you have a function that's squeezed between two other functions, and if you know that this one is going to L, and this one is going to L as x approaches a certain value, then the one in the middle will approach to L as well. So pretty self-explanatory theorem, as you can see, and we used that in the last example. A few more examples now involving limit as x goes to infinity, starting with the one at the top of the page. Okay, what is the limit of the ratio? Now the situation will get a little bit trickier. What you have here is, as a matter of fact, I think I'm going to do a few more simpler examples before I hit that one. All right, so limit of x squared as x goes to infinity. Here, you could do a graph if you like, but we should also be able to answer these questions without having to graph every single time. So as x goes towards infinity, what is happening to the y values along this curve? They're getting larger and larger, right? So y values are approaching towards infinity. And without even having to do a graph, I could say that if x is getting larger and larger, the square of x is also going to get larger and larger, and therefore the answer is infinite. And for something like this, again, I could graph it, but now I want to be able to answer these without a graph necessarily. And in that situation, we're going to basically go with the leading term approach. So infinity square, think of it as like 10, 100, 1,000, a million, a billion, and you're squaring each one of those, right? and then plus 7 times, let's say, billion, minus 27. This 27 will be negligibly small as x gets larger. So really the first term, because a billion square is so much bigger than just a billion, that even this is going to be negligibly small. So pretty much if it's a polynomial, you can determine what's going to happen to it by looking at just the leading term, because the other ones will be negligibly small. So 3 times infinity to the second power, that goes to infinity, so the final answer will go to infinity. If you have any doubts, graph it and verify the result. What about negative x plus 1? So think of it as negative of negative infinity plus 1. Think of it this way. So these are quantities like negative 100, negative 1,000, negative a million, each one being multiplied by a negative. So now you have positive quantities that are getting larger and larger. And the plus 1 doesn't change much, so the final answer is infinity. Again, you could graph this if you like, but we should be able to answer these questions even without a graph. Now, these are the situations where we have to think a lot deeper, because the top is going to infinity, and infinity minus 3, that 3 is negligibly small. The bottom is going to infinity. And before you even think about writing a 1 as the answer, stop. Infinity over infinity is not 1. We call this indeterminate. Just like 0 over 0 was not 1, right? Each different problem led to a different answer depending on the situation. That's what we mean by indeterminate form. It's going to be a different situation depending on what functions on the top, what functions on the bottom. So infinity over infinity requires a further exploration and a much slower, step-by-step figuring out what's happening. And same thing with this example on the bottom of the page. The top goes to infinity. The bottom goes to infinity. So once again, indeterminate form. So for those kinds of problems, when you have a rational function with a polynomial on the top, polynomial on the bottom, as an x goes to infinity, there's actually a little trick that we can use. So instead of having to look at the graph every time, the trick is you multiply the top and the bottom by, well, let me say it this way. You divide the top and the bottom by the highest degree term of the denominator. So we're going to divide the top and the bottom, in this case, by x. That's the same thing as multiplying by 1 over x, right? So I'm going to multiply this side by 1 over x. We're dividing by x, and this side by 1 over x. And if you simplify, the top will just be 2. And the bottom, distribute the 1 over x. You have 1 minus 3 over x. And now take a limit as x goes to infinity. The original question was infinity over infinity, but now we have 2 over 1 minus, where does this go as x goes to infinity? Top is a constant, bottom keeps getting larger, ratio is 0. So therefore our final answer is 2. So it was infinity over infinity when we started, but the final answer turned out to be 2. So that is how we resolve these cases. Let's apply the same technique for this problem. Okay, so the highest degree term of the denominator is x cubed, and you can disregard the number in front of it, just look at the power of x. So x to the third. So I'm going to multiply the denominator rather, by 1 over x to the third, and the numerator by 1 over x to the third. In other words, I am dividing both the top and the bottom by the highest degree term. Just take away the constant in front of it, we're dividing everything by that. And this always leads to some nice simplifications, as we're going to see here. Distribute your 1 over x cubed. In the denominator, you can have 2 minus, what is 7x over x cubed? That's going to be 7 over x squared. And then you have plus 3 over x cubed. Notice everything after the first term will end up going towards 0. And now distribute the top, x squared over x cubed, and then plus 5x over x cubed, which is 5 over x squared. And now simplify, and then take a limit as x goes to infinity. In the denominator, we have 2 minus 0 plus 0, just 2 basically. In the numerator, Okay, x squared over x cubed, think of it as 1 over x. As x goes to infinity, that is 0. 5 over x squared is another 0. So 0 over a number, the final answer is 0. So we began with infinity over infinity, right? Top was going to infinity, bottom was, but then the final answer turned out to be 0. So this is why this is really indeterminate. You cannot really tell what's happening just by looking at this. You have to explore the actual given equation, the expression, so you can determine is it a finite value, is it 0, and it could even be infinity in some situations. But now I'm going to talk a little bit about a shortcut method, even shorter cut than the one I just did. In general, when you are talking about the limit of f over g to polynomial functions as x goes to infinity, check out, compare the degree of the bottom with the degree of the top. If the degree of the bottom is higher, so think of it like having an x cube here, like the last example we had, and maybe having an x on the top, and so forth. That means the bottom is growing more rapidly than the top. So when x is like 1,000,000,000, the bottom is going to be so huge in comparison to the top that the ratios basically are going to approach to 0. So when the degree of the bottom is higher, this limit will be equal to 0. When the degree of the top is higher, the top is growing much faster than the bottom. So the top is maybe like 1,000,000,000 square. The bottom, is not even close. So the ratio will get larger and larger as x gets bigger. So this is going to go towards infinity. It can actually be plus or minus infinity depending on the coefficients, but let's just say at the moment that the answer will be infinite and we have to explore it a little bit better. And I'll do some examples about that. Assuming positive coefficients of the leading terms, it will be infinity, positive. And what happens if the degrees are the same? Like something like 2x over 3x minus 1 as x goes to infinity. We did an example similar to this early on. The way this one turns out to be is, and you could do a proof for it, is going to be take the ratio of the leading coefficients. So this one is going to go to 2/3 basically. Ratio of leading coefficients. And you could do a few examples to verify that. You could do a proof. Um, but that's what's going to happen. So from this point forward, if you see a quotient of two polynomials as x goes to infinity, think about these three simple rules. If the question didn't say to show work, you could definitely do it this way. Or even if it says to show work, it doesn't hurt to get the answer first. So later on, you have a way to check your answer. So now let's do a few examples about these shortcut rules. So let me give you a few moments. You'll be advised to stop the video for a few moments and then come back and check your answers. So hopefully you took a few moments to think about these problems. And the first one, degree of the top is smaller than the bottom is growing faster. The answer will be 0. This one, the top, degree of the top is higher than the top is growing faster, right? Everything is positive. As x goes towards infinity, this will be positive infinity. And the last one, degree of the top is equal to the degree of the bottom. Take a ratio of the leading coefficients. That's going to be 1/5. And for this example, what if there was a negative on the top? Negative x cubed, everything else was the same. What would be the result then? Limit as x goes to infinity. Again, you could do the older method, divide everything by x, the highest degree term of the denominator. Or another thing you can do is look at just the leading terms. Negative x cubed over x is negative x squared. Everything else will be negligibly small as x goes towards infinity. So now as x goes to infinity, infinity squared goes to infinity, but the negative in front will force it to go to negative infinity. So this will go to negative infinity. So remember, when the degree at the top is higher than the bottom, uh, the the coefficients of the leading terms are going to be important in determining whether the answer is positive infinity or negative infinity. And you can do a leading term analysis like I did here to determine the final answer. All right, so that does it for us. Limits involving infinity. I will try to add a few more examples, another segment later on.